So the interest is to look at the effect of dark matter in neutron star evolution. This is the outline of the work. It's divided into 4 parts. We'll look at introduction, brief methodology, we'll look at results, and then we conclude it. So the first question you should ask when thinking about dark matter is, why should we even think about dark matter? From standard cosmological theory, we know that dark matter and dark energy form about 95% of energy, mass energy content of our universe. So we are left with only 5% we have brief knowledge about. This means that we have to search for the origin of this 95%, its properties, and how it interacts with the 5% we have fair idea about. There are few evidence too about its existence through the galactic rotation curves, large-scale cosmological structures, and gravitational lensing. We know that they give some evidence about the existence of this object that we need to go after. But due to our lack of knowledge about how it interacts, its nature, its properties, many Earth-based experiments that are developed to search for this particular object has failed. Some experiments like the Xenon, Panda, and Lux, they are either in their second phase or third phases. They have all failed. The first phases have all failed. We haven't gotten any results. So there are new research gates that have been opened, and one of them is to look for a true astrophysical object. Now, the object that many people believe could help in this search is the neutron star. So we asked ourselves, why specifically neutron star? Neutron stars are the most compact object we know in our universe. So if they are born in an environment, assuming that they are born in an environment with high dark matter density, these dark matter particles will try to penetrate this object. And because the core of the object is made up of ordinary matter, densely populated ordinary matter, they will face resistance. So there will be collision between the ordinary matter and the dark matter. And if this continues for a very long time, we expect that the dark matter will be trapped into the neutron star. And if that process continues for a while, the accumulation of dark matter into the neutron star can change its structure. That will make it easier to be observed. And taking into account the advantage of astrophysical observations to Earth-based experiments, this can lead to constraints that can even help to improve the sensitivities of the Earth-based experiment. So, what to expect from my talk? I would focus on the role of dark matter in neutron star evolution and how it can lead to new constraints on its coupling and mass. And then we'll look at the impact of dark matter on neutron star observations, such as mass, radius, and tidal deformability. There are considerable knowledge about how dark matter affects the structure of the neutron star when it is cold. But the focus of this is we are going to look at when the neutron star is born, how it responds to this dark matter until it becomes mature, it becomes cold and catalyzed. So we also look at particle distribution within the star, which is a microscopic property of the neutron star matter. We'll look at the temperature distribution. We'll look at speed of sound within the star, and then how temperature influences the coupling of dark matter to ordinary matter. So basically, the work will be based on this cartoon. We'll look at a bigger star when it finishes using its nuclear fuel and it implodes. It forms this object here. We call it protoneutron star in the core. So at this stage, it captures neutrinos, heat up, coupled with external shocks from the environment. then the star explodes. Now, if the explosion is stronger enough, it has this core bouncing and start to evolve. But if the explosion is not stronger enough, it can accrete mass and form a black hole. So in the work, we assume that the explosion is strong enough, and then the star evolved through the formation of a cold-catalyzed star with that formation of a black hole. So that is the main idea of the work. And looking at this point from here to here is about 0.5 seconds to 1 second. So all the time below the 0.5 seconds, the star is out of equilibrium. We are not considering that. So we are looking at stages where the star is in static equilibrium. So we model the superfluid part, okay? We model the superfluid part, and then we use BPS to simulate the crust, the outer and the inner crust. So in the neutron star, when the density of the particles start increasing, it is expected that at some point it will be energetically favorable for a new particle to be formed. So the new particle that will be formed, there is speculation. There are no observation has proven that, but theoretically it's favorable. So people consider the presence of kaons, the presence of pions, the presence of free quarks, and then the presence of hyperons. In our model here, we consider the presence of hyperons and how it will affect the structure through the evolution processes. So how do we model the effect of dark matter on the neutron star? There are two known ways. We have the two-fluid method. The two-fluid method considers the dark matter and the ordinary matter, and their interaction is considered to be gravitational. So in that way, you have to consider two interpenetrating fluids through the TOV equations. And there is a single fluid approach. The single fluid approach, you consider that the dark matter and the ordinary matter interact through standard model interaction. So we are going to present the two results parallel and analyze them as we go. So we look at the ordinary matter. The ordinary matter, we model the ordinary matter using a mean field approximation. So we look at the hadrons as interacting through massive interchange of massive mesons. Then we introduce a free leptons to make the system charge neutral, okay? Make the system charge neutral. I have highlighted the phi coupling. The phi coupling, the phi meson has hidden strangeness. So here, the theoretical thinking is that as you increase the density, the degenerate pressure of the fermions will increase. So it gets to a point at densities such as 2 times saturation density and beyond, it becomes energetically favorable for some of the neutrons to be converted into hyperon through weak interaction processes. Then we consider a mirror dark matter model. Now, this mirror dark matter model, it is known in literature for a while, and it has been used by several authors, but in our work, we employed it differently, because normally people look at the dark matter as being a neutral particle, and then introduce it directly. We consider that the dark matter can form a neutron star in isolation, because we are looking at hot stars, and no one knows how dark matter thermalizes with ordinary matter. So we model the mirrored model as capable of forming a neutron star in isolation. So we impose the same condition from the visible sector to the dark sector. So we consider things like dark charge neutrality, dark beta equilibrium, dark baron conservation. And also, another point to mention is that we consider that the dark proton and the dark neutron are the same under the strong interaction. So we didn't introduce isospin to differentiate them. Then the coupling are fixed through the density-dependent meson-nucleon coupling. In this particular method, the free parameters are fitted through bulk nuclear properties at saturation density, at this specific saturation density. So these are the values of the coupling. And then the hyperons, we use Lopez, a work published by Lopez, where they extended this coupling to hyperons through using symmetry argument, SU3 and SU6 symmetry argument to fit them. The advantage of their approach is that we are able to reproduce hyperonic stars with maximum mass within the range of the observable, that is 2 solar masses. So the most important equation to solve is these 2 equations. For the neutrino trap regime, we fix the entropy. We fix the entropy per baron. Then we can calculate the pressure, energy density, and then temperature distribution through the star. And then when the neutrinos diffuse from the core of the star, we solve this to determine the equation of state. That is, okay. Now, the single fluid aspect. The single fluid aspect, we use the so-called Higgs-Portal model. This Higgs-Portal model, the dark matter and the ordinary matter interact indirectly through a Higgs boson. So here, the dark matter, okay. So in the last part of the equation, you see that there is a Higgs field interacting with the ordinary matter, and then in the second term here, you see the Higgs field also interacting with the dark matter. So the interaction is indirect. And this model has several advantages. It has been used to calculate the Rayleigh's abundance of the universe correctly. And when you consider weakly interacting massive particles like the neutralino, this is the interaction cross-section agrees with the constraint imposed by the null experiment, dark matter experiment. That is, you have a cross-section of about in the order of 10 to the power minus 47 centimeters squared. But in our model, we are going to vary the mass and then integrate over all the Fermi momentum. Okay, so in the dark sector too, this is the equation of, this is the most important equations we have to solve. So here we see the contribution of the dark matter here, and there's contribution of dark matter here. That is the single fluid approach. So this is how we model the structure of the star. We use the coupled TOV equations. But what is important is the highlighted point. We control the content of the dark matter that the star can accumulate, so that the star can accumulate enough dark matter to change its structure, but not to destabilize it. If you allow this, if you keep increasing the dark matter mass fraction within the star, it can destabilize it. So we control that. And for the single fluid part, we use the simple TOV equation. So let's see some results. This is how the model goes. We understand some things about the cold neutron stars. At least we know the expected mass and radius of cold neutron stars. So we constrain our model such that when the star cools to cold catalyzed configuration, it should satisfy the known constraints of a neutron star. So we have demarcated the confident contours for some of the pulses. We have the canonical star here. We have the gravitational wave stars here. And then the star measured through the NICER data, that is the 2 solar mass star, is here. Now, we see that when we start increasing the dark matter mass fraction in the star starts to shrink. Its mass and radius start reducing. So what is the physics here? When you increase the dark matter in the star, it goes to increase the total mass of the star. And we know gravitational attraction is stronger with massive objects. So the gravitational pull will be higher on the surface of the star. So what happens is that the star will have to shrink to increase its pressure because it only fight against gravity through the degenerate pressure, to increase its pressure. So this causes redistribution of particle inside, and that will reduce the gravitational mass and the radius of the star. So that is what we see here. And then when you look at the fixed entropy stars, you see that they have higher radius. And this is because the fixed entropy stars, they have temperature. There are temperature going on there, so it expands them. They get expanded, but we realize from our calculation that the maximum mass doesn't really change much. And then from the right side is when we put hyperons, when we add hyperons to the nucleons. Now you see that the hyperons actually reduces the maximum mass, because when you compare the masses here to the right side, you realize that there is a reduction of the mass comparatively. And then when we introduce the dark matter, we see the shrinking of the stars. Now, we compare our results with a single fluid approach. The single fluid approach seems to give the same result. When you start putting the dark matter, it starts shrinking, the same phases happens in there. But there is something very important here. When we look at this green and the black line, they look almost the same. But when we start increasing the dark matter content, they start deviating from each other. Where the black one is the deleptonization phase, so it has some neutrinos captured in there. So this means that the degenerate pressure from the neutrinos support the star against gravity. So it is able to fight the gravity and then reduce the impact of dark matter. But when all the neutrinos escape from the core of the star, it becomes vulnerable to gravity. So we see clearly the impact of the dark matter on it. It becomes more compact than when there are neutrinos. And here, we started varying the dark matter mass. We realized that when you go beyond 0.62, we start producing stars that have maximum masses less than the 2 solar masses that has been observed. So this put constraint on the maximum mass a protoneutron star can support when you consider the single fluid approach. Now, when the star cools down and you try to maintain the same dark matter mass, you realize that the structure doesn't change. It doesn't change the structure at all. So we start increasing it higher. We use 1 GeV, and then we saw a little changes in the structure. We put 2 GeV, and we see that there are changes in the structure. What this tells us is that when the star is cooled, it is capable of capturing more dark matter mass, heavier dark matter masses, without actually affecting its equilibrium structure. Because of the probably increase in the binding energy of the gravitational binding energy, reduction in thermal pressure, and then the compactness of the star. So we calculate another observable. That is the tidal deformability that was measured through the gravitational, binary neutron star measure. So here, our focus should be on the cold stars. For the hot stars, we model the hot stars because there are new detectors that are built to detect post-measure events. So these are some predictions. But the main focus of this gravitational wave is for the cold stars because it was detected through the in spiral phase before the measure. So we realized that even with our equation of state of hadrons, the black line, solid line, it is even soft compared to the binary that participated in this event. But when we start increasing the dark matter content, 1% to 1% and 5%, we realize that it becomes compact and it starts satisfying the constraint, the tidal deformability constraint. Now, we model for hyperons, nucleons plus hyperons, and then our results seems to be identical. We don't see any difference in the two. So we started looking for what might be the cause. Our conclusion is that because the tidal deformability is more sensitive to the outer part of the star, and the hyperons appear in the core, the hyperons would not have any effect on the tidal deformability. So this will not be a good indication to look for the internal composition of the star. Then we look at the particle distribution. How are the particles distributed within the star? Here we choose a particular star that is about 2.1 solar masses, and then we try to extract how the particle is distributed. Here we see that the presence of dark matter influences neutrino retention. And since the star cools primarily through neutrino emission and then other thermal radiation and stuff, this is going to affect the thermal evolution of the star. And another point is that the dark matter also reduces the neutron production and then increases the proton production. So this will reduce the isospin asymmetry of the matter. And this is in the heart of the stability of the star too as well. And then we realize that the dark matter also influences the appearance of particles, like hyperonic particles. It's when you put the dark matter, the particles appear earlier than they would appear without the hyperonic particles, without the dark matter, meaning the compactness it creates affects particle production as well. Now, this is when the third stage is when all the neutrinos has escaped from the star. Here, the temperature is high. That is the second and the third, the temperature is high. And we are seeing that the particle appearance are pushed towards the surface, meaning that some particles production in the star are influenced by temperature as well. And then there is another important point. Here we have muons, but in the two stages we don't have muons. This is because when the neutrinos are trapped in the star, its chemical potential, the chemical potential of the matter, does not allow the production of muons. But as the neutrinos leave the core, the chemical potential shifts, and then we can produce particles like muons. So the two stages, the first stage and then the last stage, the temperature are the first stage, the temperature is relatively small, and here is T is equal to 0. We see that we have fewer particles appearing. So we look at sound speed through the star. Now, this sound speed is not calculated directly from the equation of state. It is extracted from the star after gravity has influence on the star. So in modeling equation of state, the expectation will be that when you increase the degree of freedom, it should go in reducing the pressure, and then it should reduce the speed of sound. But if you look at these results, we see that the compactness that is created by the dark matter leaves an imprint on the speed of sound. So you see, when you increase the dark matter content, the speed of sound rather increases. Another very important point here. We see bumps when the star is cold and catalyzed. This shows, these bumps, when compared to the particle distribution, you see that the bumps appear exactly where some hyperonic particles appear. So this shows that the sound speed is a good indicator for determining the internal composition of the star. Now, for the single fluid. For the single fluid, where we look at standard model interaction between the dark matter and the ordinary matter, we realize that at the neutrino trap stage, here you barely see difference between the particle distribution. And then look at the dark matter fraction. The dark matter fraction is about 14% here. Here is about the maximum. I'm talking about the maximum. Here the maximum is about 34. Here the maximum is about 40. And then here the maximum is about 5%. Now we see that through the evolution, when there is neutrinos trapped in the system, it resists the capture of dark matter. It captures lesser dark matter. And when the star begin to deleptonize after explosion, it starts capturing more dark matter. This can be attributed to the softness of the star due to temperature due to the temperature fluctuations within the star. And And looking at the first stages where the neutrinos are captured, here, the second stage, we see that the dark matter influences neutrino retention. This will also have an impact on the thermal evolution of the star. We'll see later. Here, at the third stage, we realize that the dark matter actually throws the star out of equilibrium. It changes the particle distribution in the star. This has a very important consequence for observation because it will change the rotation speed, the angular momentum. This can change even the thermal photons that are emitted on the surface of the star, which is detectable because it is changing the lepton distribution. It's influencing the lepton distribution in the star and so forth. And when the star is cold, even though we increase the dark matter content, we see that the equilibrium state of the particle distribution remains almost unchanged. The particle distribution remains almost unchanged. So at the point where the star has, all the neutrinos has left the core of the star, would be a good point to observe if our objective is to look at the coupling, whether it is gravitational or non-gravitational. Now, the temperature fluctuations. This is the result from the single fluid. We realize that the presence of the dark matter actually leads to an increase in temperature in the core of the star. When I showed the particle distribution, we saw that the dark matter actually influences the neutrino production, which is in the core of the cooling of the star. This can be seen through cooling curves, deviation from the conventional cooling curves, and infrared telescopes can also observe this. Now, what is the physics here? When the particles in the star get compact, the distance between the particles will decrease. And so the gravitational potential energy will increase. And from the Vara theory, the gravitational potential energy is balanced by the kinetic energy. So if the gravitational potential energy is increasing, the kinetic energy will also increase to balance it. And the kinetic energy in our model can be related to the temperature. So this causes the increase of temperature. Now, when we look at the single fluid approach, this seems to contradict what we saw when we are looking at the two-fluid approach. When we start increasing the dark matter content of the star, we saw that it started decreasing the temperature, meaning that here, rather, the dark matter serves as a heat reservoir to absorb thermal energy from the star without efficiently emitting it. So this means that the coupling of dark matter and ordinary matter is very important if we want to use indirect means to make predictions on its constraints. Now, to sum it up, we studied the coupling of the dark matter and the ordinary matter indirectly through the interaction energy of the dark matter and the ordinary matter. What we saw is that when the star is cold, the interaction is very small. We have very small interaction, meaning it will not be a good point to try to determine any constraint on a star. And then when the star is young and capturing neutrino rich, it starts increasing. But the conclusion is that the increase in the coupling, it's less dependent on the lepton fraction. It is more dependent on the temperature. So here, the temperature is almost 0, and the interaction is very small. Here, the temperature is small compared to the other stages, and the interaction starts increasing. When, during the deleptonization, when the neutrinos are diffusing, the interaction increases, and when all the neutrinos leave the core of the star, we have the highest interaction. So indeed, looking for constraints on the interaction of the dark matter, we cannot rule out hot stars. So the conclusion. The macroscopic structure of the neutron star admixed with dark matter alone is not a sufficient constraint. It's not a sufficient condition to constrain the property of a dark matter. So we have to look at the young stars, like protoneutron stars, which shows to be more sensitive to dark matter accumulation, because the lepton fraction and then the entropy density regulates the coupling between the dark matter and the ordinary matter. And then from our modeling, we were able to come to a particular constraint of a sub-GeV dark matter that a protoneutron star can accumulate. And the upper limit is set to 0.26 to 0.62 GeV, using the observable constraint that neutron stars should have a maximum mass of 2 solar masses. We can impose this constraint. And then the microscopic property of the neutron star admixed with dark matter depends on the coupling. So when you have a stronger coupling, you can see more difference between them. When the coupling is weak, that is when the star is cold and the coupling is weak, we hardly see a difference. This is a new research area we are veering into. There are no many work in this area. So there is hardly some other works that model effect of dark matter on neutron star vis-a-vis the structure of the star, modeling of the star, aside the theoretical prediction. So we propose that other people too could try to model such characteristics of the star, looking at different dark matter, like the bosonic dark matter, axiom dark matter, feebly interacting massive particles, and weakly interacting massive particles, so we can compare results and impose more constraints on the dark matter properties. So thank you, my collaborators, my supervisor, and thank you all for your attention.
I've got one question about, like, at some point you spoke about your models, you know, like when the Lagrange, you showed the Lagrangians, the interaction terms, and you said something about, you know, the spin and eigenspin degrees of freedom that were not explicitly included. And so I was wondering, like, what was the motivation behind that? Like, could you tell us more about, like, why you think that these degrees of freedom do not have a role and impact in what you're doing?
Okay. Here we are looking. It was omitted only in the mirror dark matter model, and the whole idea is that no one really knows about the properties of the dark matter, and we are looking at dark proton and dark neutron. Okay. Putting an isospin projection is another degree of freedom you are introducing. Okay, so not knowing exactly the properties of these two particles, we decided to treat them as identical under the strong interaction. Okay, so it is not possible to differentiate between dark proton and dark neutron under the strong interaction. But in the model, like we consider it being negative and positive charge and all that.
I see that you have a mass term and an Higgs interaction in your Lagrangian. Shouldn't the mass come from the Higgs interaction?
Okay, this is a supersymmetric model. This is a supersymmetric model. So the mass comes from the dark matter. It comes from the weakly interacting particle.
Okay, thanks.
Yeah, I have the question concerning the accretion of these dark matter, because you have to get the dark matter into the star. Yep. And I remember the argument that there are no dark matter in stars, because that would be in all also ordinary stars, is that you need some kind of interaction. Because if a dark matter particle goes in without interaction, only does elastic scattering, it will also get out again. Yeah? So you cannot accrete the dark matter. So do you have some limits of the cross-section, some upper limit in order to get the dark matter at all collected in the star?
Okay, from this particular model, the upper, if you calculate the cross section, it is in the order of 10 to the power minus 47. And in terms of the dark matter being able to get out of the star, the escape velocity of a neutron star is about 0.6 speed of light. So that the probability of them all getting out is very small. So if it continues, the process continues for a very long time, it should be able to accrete enough to change the structure. Another thing is that doing it through this single fluid, that issue could arise. But in the two-fluid approach, you are looking at the dark matter and the ordinary matter as predicted by cosmology, interacting through gravitation. At least that is how we see it, the natural way we see that the dark matter interacts with ordinary matter. It should be through gravity. So we show the two-fluid tool. It is quite new, this model, from 2015. It started gaining ground from 2015. It shows that really, even through that approach, it is able to accumulate enough dark matter that can change the structure of the star.
Question to that, I mean, maybe you mentioned it, I missed it. In principle, after a long time, all the dark matter should be really in the center of the neutron star, or not?
Yes.
Yeah. And that should also be the case for normal stars, yeah, because they also will accrete dark matter. How would that affect normal stars then in this case? Okay,
that comes from the compactness. For the normal stars, we believe that the probability of the dark matter getting out is higher, looking at the density within the star. But for the neutron star, due to the density of the particle and the compactness, the probability of them getting out is quite less. So it becomes the natural go-to object to look for some of these things.
So maybe I have a question. I'm here.
Okay.
So is there any, I don't know, distortion signature coming from the merging of the neutron stars that can highlight any, let's say, presence of dark matter?
Currently, no.
Currently, no.
Currently,
okay.
no. But as I showed from the tidal deformability, it actually compactified the star. So with the future, the improvement in LIGO, the coming up of the Einstein telescope and the Cosmic Explorer, which are determined to observe post-measure events, probably we can see a signature of dark matter, comparing several major events.
Okay. Okay, thank you. Is there any further questions? No? So we thank again Adamu, and we move to the last speaker.